Κυρίες και κύριοι, ο κύριος Kent Peterson.
Gentleman, Kent Peterson.
Distinguished guests, ladies and gentlemen, it is my sincere honor to be here today to share a perspective that's one of a practicing engineer from the state of California in the United States relative to not only efficiency in buildings, but also high-performance green building design. There's no question that in the United States, California as a state leads the nation not only in energy efficiency in buildings, but also in green building practices within the United States. And that's the perspective I would like to bring this morning. High-performance building design starts with proper site planning for the building site. Design for water use efficiency, design for energy efficiency, minimizing the building's impact on the environment from the materials and resources that are used, and good indoor environmental quality. But it's my experience that good design by itself generally does not result in high-performance building operation. We must address operations. We need to better equip building operators with the tools required in order to maintain high-performance building operation for buildings that are designed for high-performance buildings. There's many standards and rating systems that are out there today relative to green building design. One of the most popular ones in the world is probably U.S. Green Building Council LEED certification for buildings. BREEAM in the UK, DGNB in Germany. There's many other popular ones that I don't show up there. But this is an attempt to really start to understand the various aspects of green building design. Now, Standard 189.1, which is an ASHRAE standard that was developed back in the year 2009, is a standard that was developed under a consensus basis that was intended to be put into building codes in the United States. And this standard has since our green building codes within some of the states in the United States. It was a collaborative effort. It was done not only with ASHRAE, but it was done with the U.S. Green Building Council and the Illuminating Engineering Society of North America to help reduce the impact on the built environment. And there's no question in my mind that the provisions that are included in this standard can reduce the negative environmental impacts through high-performance building design and operation. This standard not only addresses the design side, but addresses how to actually turn a building over to the operators and the building owners to operate the building under high-performance building operation. Performance definitions are really important when we get into high-performance buildings, and it's really about how we define. I look at this as three tiers, starting at the top level tier, which is really defining the objective that an owner may want when we talk about performance in a given performance metric. And that may be to, if we talk about energy, to minimize energy consumption for building operations. As we start to move down and get into more detail, we start to develop performance goals for a given project. And this is really a specific statement of desired level of achievement for that given building. And that, an example might be to reduce the primary energy consumption for the building operation by 30% compared to a standard that may be out there in the industry. And then we get into performance metrics. And if we have the goal, we want to actually define a metric by which can be measured to determine whether we're successful in achieving that goal. And a metric is really something that's a measurable quantity by which we can measure. And in this case, it could be the net source energy use intensity of the building is 30% savings compared to a specific standard that's applicable for that building. We could actually define per unit area of how much energy that building's going to use based on how we know the building's going to be operated during the design phase. Now, integrated design process is also a very important aspect that we find in the United States in order to provide high-performance buildings at a very similar cost, meaning not at a cost premium to get the performance we're looking at. And this is really team-based collaborative thinking which is a method that conscientiously moves towards more open and transparent agreement amongst the various stakeholders that are involved in the design and the operation of the building. This would include the building owner and the architect and the various engineers and the consultants that are involved to look at the various aspects of what the measurable goals for performance are, and really working towards converging on project outcomes rather than just individual goals for a given discipline. And if we can do this collaboratively, this is how we can actually accomplish this without an increase in construction costs many times. Now, the advantages are, for integrated building design, it has to start at the very beginning of a project, when we're in the conceptual side of a design of a project, in order to see the greatest benefit. And this little graph up here really shows that the greatest leverage, we lose leverage as we move down. As we start to be collaborative, when we get into close to construction documents or detailing of the design, we really lose that value opportunity that we have for having this collaboration. So the benefit really comes at the beginning of the project. And the third concept in integrated design is really cost transfer. And the concept here is that if we can make the right architectural decisions at the beginning of a project, that some of the most important and simplest upfront architectural decisions about the building's form, its orientation, even its architectural style, can have some of the greatest long-term benefits on not only the HVAC system, but the lighting systems that go into the building and the daylighting that we actually accomplish from that. And so we want to be able to do that and use the money more wisely by making the right decisions through an integrated approach with the whole design team. Modeling is also extremely important when we get into high-performance building design. And today, there's so many different analyses that can be performed that we were not able to do even 10 years ago. Building information modeling, or BIM, based performance analysis allows exploring possibilities with different design opportunities, including climate understanding, building massing, orientation, during the conceptual stages, to see some of these ideas that we talk about from an architectural standpoint that can help reduce the size of the mechanical systems and some of the electrical systems that feed those mechanical systems, and allow us to have that cost transfer. Now, as the design develops, analysis such as daylight, water review, even heating and cooling loads, energy modeling, and renewable energy use can all be modeled using this type of BIM energy performance analysis available today. Now, we talked about the various aspects of high-performance building design, and site sustainability is really the first area where this is an important aspect that we look at. And of this, we can divide it into some key areas. One is the site selection on where we actually choose to build a new building, if it happens to be a new building. And if we can pick a location that is on an existing development, certainly what we refer to as a brownfield site, there's benefits in not having to develop on a greenfield site from a site selection standpoint. The design to reduce the heat island effect, many things that are in some of the standards that are out there today, 50% shading of the site hardscape to try and reduce the heat island effect. And heat island effect is having a large effect on HVAC loads or cooling loads in many metropolitan areas. Cool roofs were appropriate in certain climate zones. Even promoting partial shading on the east and west exposures where applicable are good strategies to reduce the heat island effect. We also want to reduce light pollution. Light pollution has become a very large problem around the world, especially if you were to look at some of the images from space looking back on the Earth. Outdoor lighting power densities are now being reduced in our standards. We've also are looking at maximum allowable backlight, uplight, and glare fixtures to make sure that we are not spreading the light up into the sky. And then finally, trying to manage the rainfall on sites. We design new building sites to maintain at least 50% of the available annual rainfall in the development footprint through infiltration, reuse, and evapotranspiration. So we really try and absorb that moisture back into the building site without not allowing it to run off the building site wherever possible. A second issue is water efficiency. And it's said that water really is life on Earth. And from my perspective, coming from the state of California, water is almost becoming more important than energy itself. While we're spending a lot of effort in reducing energy consumption in the state, our state now has 33 million people in the state. And in the southern part of California, we have more than half of that in the southern part. And the southern part of the state is not, we do not get rainfall very often. It's actually more of an arid desert environment in the south part of the state. So we're really looking at ways to reduce the building's impact on water use as much as possible. And that really has two factors: the site that the building is on and the building itself. And when it comes to site water reduction, there's many things: biodiverse planning, hydrozoning, so we can ensure that we actually are creating landscaping zones that use similar type water requirements, trying to actually plant native species that can grow without water, using just the amount of water that's available through the natural rainfall that's in that area. And smart irrigation controllers are now required by our building codes on any building developments that are out there. When we talk about smart irrigation controllers, the smart irrigation controllers know they're measuring the actual density of moisture in the soil. They're knowing when it's going to rain, and will make decisions on whether the irrigation systems will actually come on. Other things we're doing for building water use reduction, very similar in many parts of the world that I visit. Low water consumption fixtures and appliances are now required by our building codes. We're also starting to limit cooling tower cycles of concentration. So in the HVAC arena, one of the larger areas where water consumption is used is the evaporation of water in cooling towers and the blowdown of that water in cooling towers. And so cycles of concentration are usually being limited. If we're greater or less than 200 ppm water hardness, we're going to limit it to 5 cycles of concentration minimum. And so we would like to see higher than 5 cycles of concentration. And if it's greater than 200 ppm, we're still have at least having a minimum of 3.5 cycles of concentration on the cooling tower to try and get the most use out of that water before we blow it down and send it to the drain. Now, the next is really optimizing indoor environmental quality. And if I'm going to focus in 2 key areas for high performance buildings in this conference, it's going to be on indoor environmental quality, and it's going to be both on that and building energy efficiency, since this conference title is Efficiency in Buildings. I have to say that while high performance buildings really involve many considerations, when it comes to the HVAC sector, these are 2 of the most key sectors that we need to focus in on. Now, near the start of a project, I do want to say that comfortable in indoor environments is more than just indoor air quality. It's really what we refer to as indoor environmental quality, which has to do with the natural light that we provide into the spaces, proper ventilation, appropriate temperature and humidity ranges, and localized controls where the occupants actually have control over their thermal comfort that's in the space. The bottom bullet on the slide is extremely important because I've actually done several conferences where we talk about deep energy savings into high performance buildings, but energy savings should not be at the cost of a good indoor environmental quality. If we want to have a good energy efficient building, we can't forget the fact that we're actually building the building. We're designing buildings for good indoor environmental quality. That's the purpose of the building. The building is not being designed to save energy. That's not the purpose on why we actually construct buildings or design buildings. It's really to provide that proper environment for what needs to occur within the space itself. There's conditions that actually promote both health and comfort. And we discuss occupant health and comfort with building owners in order to define the criteria to be applied to the project. The following areas are really key areas that need to be covered in those discussions: indoor air quality, thermal comfort, visual comfort, and acoustical comfort. There's some very good resources that are available that are free, and I always like to at least let people know of the free resources that are out there. This is one that's available through ASHRAE at the ASHRAE website. The link is available on the bottom of the slide that all of you will have a copy of. But this is an indoor air quality guide that goes through all the various important components when actually designing for indoor air quality and operating a building to maintain good indoor air quality inside the buildings. And there's two key aspects: controlling the contaminants in the air supply, but also limiting the indoor air pollutant concentrations that are within the building itself. There's a couple other very good references that some of you may not be aware of, but ASHRAE Standard 62.1, the 2013 version, provides nominal guidance on minimum requirements for ventilation. This standard is referenced in many high-performance green building standards, and it's also referenced in the LEED rating system. ASHRAE Standard 189.1, which I talked about earlier, which is the design of high-performance green buildings, goes a step beyond ASHRAE Standard 62.1 for providing even better thermal comfort inside the space and better environment. And you could actually see the requirements in one of the sections on indoor environmental quality within that standard. Now, ASHRAE Standard 55 is our standard on thermal comfort. And this is a very good standard that's been written many years ago and continuously is updated. But this provides for thermal comfort and looking at things like metabolic rate, the clothing insulation value of what's expected inside the space, air temperature, the radiant temperature, airspeed, and humidity, and the impacts of each on each other. So if we're looking at things like passive strategies, the airspeed can have a good impact on expanding the thermal comfort range within that space. So one of the things to consider always is to increase the space temperature deadband for the occupied mode as an energy saving strategy that might be utilized to save more energy. Visual comfort is also extremely important. Light levels that are too high or too low is going to cause eye strain and loss of productivity within the space of the environment. This means that you have to have proper design for daylighting within the space. Sometimes too much glare from improper design of daylighting will provide eye strain, and that's not going to be good for the occupants. We want to avoid the direct sun penetration into the workplace. Low color rendering index, which is referred to as a CRI, and low correlated color temperature, or CCT, really reduces the visual acuity and puts strain on the human eye, which leads to fatigue. So we want to try and maintain a higher CRI and a higher CCT in the space in order to have a better indoor environmental quality from a lighting perspective. And the last component on indoor environmental quality that I'll talk about is really about acoustical comfort within the space. So we talk about thermal comfort in the space, but acoustical comfort is also very important. We want to know what the ambient noise criteria is for each space, required in certain offices or sensitive areas of a building. Occupant created background noise. We have to have an understanding of what that background noise is going to be and what noise level for speech intelligibility that's going to be in the space itself. So these issues really need to be defined as some of your metrics in defining IAQ requirements for high-performance green buildings. So now I'd like to move into optimizing building energy efficiency, which is what this conference is really about. The first step, in my opinion, in the process is really to determine how energy will be used in the building. No two buildings have the same breakdown in their energy usage chart, and it's determined by many factors. This is just one example of looking at energy within a building. What we see here is office equipment, a plug load, air compressors that might be in the building, motor loads, the cooling loads that are in the building, how lighting is being impacted, and how much heating impacts the total energy consumption that'll be used on an annual basis. This is really important to start with on a building design, because we don't want to spend too much of our effort focusing on the small 2% of energy or the 5% of energy. We need to understand a given building, where it's going to be located, where most of our effort should be spent on trying to reduce the energy, so we can put our efforts in where we can get the most value in the end. Again, free reference material is always valuable. ASHRAE does have the Advanced Energy Design Guides, if you're not aware, that are free, available to anyone to download off of the ASHRAE website. You don't even have to be an ASHRAE member to download these guides. In fact, we've had over 500,000 guides downloaded to date from the website, and this guidance is good for architects and building owners relative to very many different building types. But we have currently guides that will reduce from the United States energy codes, 50% energy reduction is our current set of guides are. So when we speak about 50% energy reduction in the United States, we're talking about total energy, not just the building envelope and the HVAC and the lighting systems. We're measuring actually with the plug loads that are in our building stock also. So these guides really do have some good starting points for building envelope considerations in different climate zones, types of HVAC systems, types of daylighting strategies, lighting strategies that are good starting points. This isn't the end-all solution by any means for high-performance building design, but if you're looking for good starting points, there's good prescriptive information in these guides that becomes useful for different specific types of building types that you might run into out there, including office buildings, schools, retail buildings, and hospital buildings is what we currently have guides for. So studying climatic data really helps to inform and evaluate the design of passive strategies and assist in the planning of renewable energy sources that are going to be available for a given building project. It's very important for us to be able, as engineers, to assess the frequency of occurrence on an annual basis of what's really happening from a climatic perspective in order for us to analyze passive strategies and the ability to really reduce energy consumption by maybe applying passive strategies that we might end up with a hybrid solution with active and passive strategies in our building designs. There's things out there that allow us also to help understand really what's happening. This happens to be a psychrometric chart used with an ASHRAE psychrometric program that can look at the climate, it looks at the climate zone that we're in. It plots the number of building operating hours on the psychrometric chart, both the dry bulb and the wet bulb temperatures, so we know really what's happening, and then puts the indoor thermal comfort zone in there so we can get a visual perspective of what the possibilities are for potentially looking at different types of passive strategies. Other tools that are out there allow us to look at climatic data on a monthly basis, looking at the highs and the means and the lows. Many of these now are web-based tools that are available to us to understand climate in a given building area. This one allows us to look at not only diurnal temperatures, but mean radiation, diffuse. So if we can look at all of this data, it really gives us that ability to start to dive deep into energy savings. And diving deep into energy savings is about two things, really. It's about using passive strategies, and it's also about the reduction of the size of our mechanical systems that might be in those spaces, so we can get that cost savings that we looked at initially, both on the mechanical and electrical side, and put that into the building envelope. It's very important when we look at deep energy savings on understanding the goals that we talked about early on and being able to define the goals as an entire project team that's going to be available. I think it's the time and effort that is spent by the building design team to achieve this level of efficiency that we have to also understand still has a high risk of not accomplishing high energy efficiency if we can't communicate to the building operator what's going to be required in order to accomplish this from an operational standpoint. So while we can do things, if it's not capable of being operated by the building operations staff to that level of efficiency, we will not accomplish the goal that we're looking for. And this becomes important because not all building operators are the same. We have certain building operators that have certain capabilities. where we might want to stop at a certain level, accomplish 95% of the efficiency we can get, understanding what their level of operations is, versus going that extra 5% that might make it too complex to accomplish the energy efficiency savings. Now, when it comes to energy saving alternatives, the major focus really has to be in the following areas: the building envelope, lighting, plug loads, HVAC systems, and service water heating. Increasing insulation to lower thermal transmittance values like the U factors for more thermal mass that might be in the walls and the roof are all beneficial when we're trying to look at the building envelope. Cool roofs with high reflectivity in climates with more intense solar radiation are beneficial to the cooling loads that we'll see on an annual basis. Considerable effort really needs to be focused in on the fenestration or window designs in order to ensure proper balance among heating, cooling, and daylighting requirements for the building, because they will all impact the annual energy use that are going to occur in that building. And then even orientation-sensitive window-to-wall ratios are recommended to help control the solar heat gains while allowing more visible transmittance of light to orientations where possible to accomplish the daylighting savings that we'll see on an annual basis. And finally, the placement and integrity of continuous air and vapor retarders, which I know is going to be discussed in one of the breakout sessions today, is extremely important and now required in the building codes in the United States. It's been a long time coming, but we now have it required in our building codes for continuous vapor barriers on our building designs. Passive design strategies become very important and are really considered early on since they impact the early architectural decisions of the building. Passive strategies are usually employed to provide heating, cooling, ventilation, and lighting. If we can understand the dynamic nature of climate is key to designing these strategies that are capable of responding to and optimizing the beneficial use of climate when it's available, and limiting the detrimental effects of climate when it's a liability on the building itself. There's many strategies that are being employed right now, and not one of these strategies is the correct strategy for every building. It really is dependent on the building and the climate that we're actually in, on what's going to make the most sense for a given building design. We're also putting a lot of effort currently in the United States and in California on reducing plug loads within buildings. This is something that was considered in our building codes as unregulated loads in the past. Our building energy codes relied primarily on regulated loads, which was building envelope, mechanical and electrical systems that are in the building, but those electrical systems really focused more on the lighting power that was being used and not the plug loads. This is now changing as we start to transition towards net zero energy. We have goals in the state of California that all new residential developments will have to be net zero energy by the year 2020, and all commercial building developments by the year 2030 will have to be net zero energy. And as we do that, our building energy codes will now address plug loads. So the current code that's coming out on January 1st of this next year is one step in moving towards addressing plug load and plug load reduction within buildings, having occupancy sensors that turn off a certain amount of the plug loads when no one is in those areas. This slide is simply something to give you a feel on how plug loads can be impacted with simple decisions by the building owner. While this may not be under the design engineer's purview during the design, if they're designing the HVAC system or the lighting system, if you're truly serious about high performance building operation and deep energy savings, and trying to accomplish net zero energy, we must address plug loads. And simple things here, even as simple as voice over IP phones versus a regular conventional phone, sorry, the one on the right is actually a conventional phone. When you take that and you multiply it by 8,760 hours in a year, that ends up to be a lot of kilowatt hours when we look at these types of strategies. And so anything we can into the building operation help us reduce the amount of renewable energy that's going to be required in order to accomplish net zero energy. HVAC system considerations. We want to reduce loads significantly. A big energy consumer in commercial buildings is heating air it's heating air that's already been cooled down. A standard might be a variable air volume system with reheat, where we're actually doing a lot of reheat, and we're trying to reduce the amount of reheat in many of the buildings that are out there. Certainly, low exergy systems. Looking at IEA Annex 37 and the ability to consider radiant heating and cooling or dedicated outside air systems or displacement ventilation, where we're actually using low-grade, low-temperature heating systems or high-temperature cooling systems, has a lot more ability for some of the strategies where we can actually have passive strategies that implement these active strategies and use a lot more energy, or use a lot less energy to maximize our energy efficiency. It's interesting that sometimes we get lost in the cost of energy efficiency. Recently, just 2 years ago, the United States General Service Administration, and in the United States, the General Service Administration is the largest owner of building stock in the United States, had commissioned me to evaluate what was the true cost of actually going to the highest level of energy efficiency on a given office building that they would build versus the minimum code required efficiency that was in that building. And believe it or not, it was only $50 per gross square meter of the building to get to the highest level of efficiency that was available on the market today. And that was all equipment, from the air handlers to the chillers, and included oversizing the air handlers to make them have less face velocity, reducing the overall static pressure, going to the highest grade efficiency chillers, the highest grade efficiency cooling towers, and the cost was minimal. I mean, this translates on a square foot basis to $5 per square foot. We're building buildings in the United States, especially the General Service Administration, where they're probably spending closer to $25 a square foot just on the marble that's going into the lobby. And so we have to put some of this in perspective on this is not very much cost. And if we can do the things that we talked about earlier through integrated building design, which is actually to lower the size of the mechanical system and reduce the size of the electrical system, we have these savings where we can easily put it into going to higher efficiency equipment that's above and beyond what's required by the building codes. In wrapping up, we have to measure what we want to manage. There's no question. There's some another good document that's out there, the Performance Measurement Protocols for Commercial Buildings. If you're interested on how the United States is looking at some of this, this was done with the U.S. National Laboratories and ASHRAE on how to measure energy, water, and indoor environmental quality. One of the aspects we're getting into in detail right now is thermal comfort, indoor air quality, lighting, daylighting, acoustics, and even the biometrics of individuals that might be in the space. We're starting to analyze this at a federal level to do some research to decide what kind of building labeling can we do on the IEQ side. We're already doing building labeling, like many of you, on the energy efficiency side and on the water side. We want to now start to look at how we can actually integrate indoor environmental quality into the labeling systems of what we're measuring. The measurements usually are the sub-meter level to HVAC, lighting, plug, and vertical transportation. We're seeing almost commonplace now building dashboards where we can actually visually see how a building's doing. In some cases, some buildings might compare themselves against other buildings if they happen to be in a building. So you can see not only how the building is performing at this site, but how it's performing relative to the portfolio that might be out there for the buildings they're looking at. And lastly, really building commissioning is extremely important to help accomplish, achieve, verify the document. Talking about building commissioning, but building commissioning is so important that currently in California, 2 years ago, it was put into the building code in what we call our green code. And then just recently, it's now been transitioned to code that we mandate commissioning on any building that's over in order to accomplish the energy efficiency that we're looking for by having building commissioning in the code itself. I'll close in saying achieving high performance and low energy buildings requires a vision, goals and measurable metrics that we talked about, integrated design, attention to detail, and I think we have to plan for high performance building operation if we're going to accomplish it after the building's constructed and put into operation. And I would also like to close by saying that it is possible to build and construct high performance buildings that don't cost any more money than the normal buildings we design with these types of strategies. Thank you.
Thank you very much, Mr. Peterson. Ευχαριστούμε πάρα πολύ, κύριε Peterson.